terms of the Mandela effect, what a meter is and what a meter has always been. Now, those of us who are in Mandela effect experience, you sometimes notice dilations in time where time seems to have slowed down or quickened up. Now, this might surprise you, but the way they measure the meter is not independent of time. What they're doing, they're actually using time and speed to define the meter. Now let me go through the history of the meter. So it says here, going back to the 18th century, at that time there were blah blah blah. So anyway, they decided to say, right, someone suggested the length of a pendulum having a half period of 1 second. Others suggesting a meter 10 millionth the length of the Earth meridian along the quadrant, and so forth. So it's based on the meridian of the Earth, and I think at some point it was the meridian through Paris, from pole to equator, which is 1/10 to the -7th of that. Yeah, but this was out by 0.2 millimeters. Yeah, as you can see there. Yeah, so basically then they moved on to define the meter different. Started using platinum alloy. Yeah, so they got a rod of platinum, and they decided to say, right, that would be what the standard meter was. Yeah, and then they decided to measure it at the melting point of ice, because obviously metal expands when it's frozen and so forth, and contracts. Expands when it's heated and contracts when it's frozen, I think, or vice versa. I'm not sure. It depends on what you're using. I'm not sure what it is for platinum. Then moving away from platinum, they actually started to go into radiation. Yeah, they tried platinum at in different atmospheric conditions. Then they went into radiation, so they started using we'll get to krypton. Yeah, so they started using the wavelength of krypton to define what a meter was, and the guy, I think Michelson was his name, he won an award. I think he won a Nobel Prize for it and everything. Then the last definition of a meter, which we have at the moment, the meter is the length of the path traveled by light in vacuum during a time period of 1/300 millionth of a second. So they're actually using the second to define the meter, the second and the speed of light to define the meter. They haven't defined it independent, as an independent measuring unit. Now this is very suspicious to me, because what's happening now, when they came up with this definition in 1983, the reason they did that is because in 1983, that's when they came up with an exact definition of the speed of light. In 1972, where they got that 300 million value, the speed of light up to 1972 was within plus or minus 1,000th of a meter squared. Yeah, so it had not settled down to an exact value. It was still fluctuating plus or minus 1,000th of a speed unit. Yeah, so now that's not accurate enough for you to say, right, that's the final value of the speed of light, and we'll use that to define the meter, because that's like saying now the error of that is like basically looking at a car and saying, right, I don't know what a meter is, but whatever speed that car is moving, yeah, if it travels from point A to point B, yeah, that's how long a meter is. Yeah, and obviously if we want this car to travel for 1 second to define what a meter is. Now this car could be traveling at 10,011 meters per second. If a car traveling at this speed travels for 1 second, it would have traveled more than this, the distance that this car would have traveled in 1 second in case 1. Yeah. So this car traveling for 1 second would have traveled less distance than this car traveling for 1 second. You can see that. So if the speed of light is fluctuating, yeah, it could be this speed or that speed. So the meter can be that long or that long. Yeah. So I don't think that was accurate enough for you to say, right, we've reached the final value of the speed of light, that we can use it to define the meter. I don't think it was. Yeah. So basically, what I suggest is a new suggestion I've got, is to go back to 1972, and you don't give up. You don't say, okay, this could be exact if we define the meter using that value. You don't give up yet. You go back to the meter itself. Yeah. Right, and you choose an atom. Let's say an atom whose diameter we know to be in the region of 1 nanometer. Yeah, I think atoms will be in the region of nanometers by now, isn't it? You could find one which has a diameter of a nanometer or close to it, and then just say, right, even if it's close to it, even if it's like 1.5 nanometers as you know it, you could say, right, no, we'll call that 1 nanometer. Even if it's 2, the closer to the nanometer, the better. We'll call that 1 nanometer, right? Then you take that atom and you line up 1 billion of them in a straight line. The technology to do that, we'll need to discover it, or we need to improve upon it. And then you measure the distance from one end to the other, and that is your universally recognized 1 meter. That's all you need to do. Yeah. And then you have a universally recognized 1 meter. Obviously, in different temperatures, the radiation of the radius of the atom might contract and expand, I suppose. But you can use a physical entity to measure, to define a meter. Yeah, and then the inaccuracies would depend on how close we can get the value of so how packed we can get the 1 billion of these atoms to be in a straight line, which are in a straight line. You make it as straight as possible, so straightness is also an error accumulator, and compactness. Yeah, so the straighter it is and the compact it is, and that gives us the most accurate meter to date. Yeah, so we need to go back to the drawing board and define the meter which is independent of speed and time, because that's a bit ridiculous. Yeah, and like I told you, saying that regardless, I don't know what the speed of this object is properly, but whatever speed is traveling, yeah, if it travels for 1 second, that's how much a meter is. It could be that speed or that speed. We had not reached a final value because that error there is a bit too much. Yeah. And considering you said when you measure dilation is in ranges much smaller than this error here, that's a bit too much. Yeah. So my argument is that we can go back to 1972, start from there, and then try and figure out a meter which is independent of time and speed. Yeah, if it's not independent of time and speed, that's ridiculous. So